with naming ions, if we're figuring out if it's an ionic compound, what two types of elements need to be there for it to be ionic? And what else? A metal. It has to be a metal and a non-metal to be ionic. You need one of each. If they're both non-metals, that's covalent. So if we look at that first example of carbon dioxide, what is carbon? What is oxygen? So two non-metals, that means I'm going to just abbreviate this as NM. This is going to be covalent. What about the next one? What is potassium? It's a metal, and then chlorine's a non-metal. So this is good. We have a metal plus a non-metal, which is ionic. So you guys have to get used to realizing which is which because they're named differently. And so we're going to go through that naming process today. And so what we're going to have is different classes, and I'm going to bring back some terms you guys have heard before. Ions can be monoatomic. And with some experiences with prefixes, what does mono mean? One, atomic, think of it as atom. So these are going to consist of a single atom. So we can have monoatomic ions, and if it's an ion, it's going to have a charge, and it can be positive or negative. So we're going to go through the cations first and talk about how we name them. And so what you're going to do is you're going to use the name of the element. And then the only other step is you're going to just add ion after it. That's all you have to do. So if we're looking at lithium, when it forms its ion, it's a lithium ion. Sodium, it's a sodium ion. So super easy to name monoatomic cations. Now talking about where these live on the periodic table, I'm going to kind of go through and highlight them. So we have lithium, sodium, and potassium. And if I highlight where they are on the periodic table, it should be no surprise that they are in the same group. They all form a +1 charge. Therefore, they're in group 1 because they have their 1 valence electron that they like to lose. Now, if we look at beryllium, magnesium, calcium, strontium, barium. Beryllium, magnesium, calcium, strontium, barium. No surprise that this is going to be our +2. They have their 2 valence electrons. And so then we have these other 3 that you guys will get used to working with. Silver, zinc, and aluminum. Now, if you look, it's a +1, +2, +3. Where these lie on the table, if we were to continue labeling the top of the groups, I've labeled them +1, +2. The next would be +3. And aluminum falls under that +3 row. If you go diagonally back 1, here's zinc, which is +2. And then diagonally back again, we have silver, that's +1. So if you can somehow remember that we have this trend of +3, +2, +1, and a backwards kind of diagonal, will be helpful. One thing I do want to mention about, I'll zoom out a little bit, these charges. Do you notice how, for example, aluminum, it says Al3+. That means the exact same thing as what we've been writing as +3. This is just typically, for whatever reason, how they write it in the science community. Both are accepted, but if you see me write it either way, it doesn't matter. Or if you write it either way, it doesn't matter which side the sign is on, as long as you have the right sign and the right number. So those are the same exact thing. Any questions about naming cations? This one's not too bad. Sweetness. Let's talk about monoatomic anions then. So typically how you name ionic compounds is you say cation and then the anion. And so if you're thinking about connecting this to kind of the trends we saw with covalent, what was the ending that the second element always had? Ide. Notice how all of these have ide as their ending. So that system is going to kind of show up here. And so for the naming rules for anions, what you're doing is change the ending to IDE. And then if we're talking about the specific ion, you just add ion. So now we have the fluoride ion, the chloride ion, etc. And so talking about where these live on the periodic table, if we look at all of the ones with a -1 charge, those are all the halogens. They live here. Then the ones that have a -2 charge are one to the left. And nitrogen, one more over. So if we're thinking about making these connections, again, back to valence electrons. So if I put valence electrons in black, 1, 2, 3, 4, 5, 6, 7, 8, and you remember that we want the octet, how many electrons is nitrogen away from having 8? 3. If you add 3 electrons to something, remember we're adding that -3 charge. So this is why nitrogen's -3, why oxygen and sulfur are 2, why the halogens only need 1 more electron. So this is where that negative charge is coming from, is how much to add it on there. Any questions on monatomic anions? Sweetness, okay. Now, when we have, so these are the elements that are nice. They typically, like almost 100% of the time, always form these charges. When we start working with transition metals, they can form more than 1 charge, and this is where it kind of gets a little tricky. But how we name these, and so one thing I'll draw attention to is I'm just going to highlight this little statement here, that these are the ones with more than 1 possible oxidation number. Remember, oxidation number just means charge. And so we'll start with copper. We have copper that can form a +1 and a +2 charge. Here's where copper lives. And the way that we denote between the two is using Roman numerals. So if it forms, an element can form more than 1, you must use Roman numerals to indicate charge of ion. And so usually, I mean, the highest you'll ever really go is probably 7. So just a refresher, 1, 2, 3, 4, 5, 6, 7. So just a refresher, just in case you're not the best at Roman numerals. All right, and so then we're also going to look at iron. Iron forms 2+ and a 3+. And so does cobalt. Cobalt has that same option of forming +2 or +3. And this is where those two live. And for purposes sometimes to remember which ones typically form +2, +3, if you look at it like COFE, it's kind of like coffee. You're like, knowing me, I'll have at least 2 or 3 cups of coffee. The charges are at least 2 or 3. I don't know. Cheesy way to try to remember it. And then we have tin and lead. these make +2 or +4 charges. Or they live are over to the right here. So the only really big difference here, so they're still cations. They are still forming plus charges because they're metals. But because these cations can form more than one charge, the only difference with the naming is using Roman numerals. But I do have to mention, when we start actually putting compounds together with, or anions together, this is a common mistake. Oops, as if I could spell common. And that's what I'm going to tell you is do not use Roman numerals to indicate number of atoms or ions. Let's do ions. And so I'll bring up this mistake again. It's doesn't really apply when we're just talking about a single ion, but when we start combining anions with cations, it's a common misconception that 2 represents actually how many are in the molecule, when it's really just the charge of an ion. But I'll bring that mistake back when we start actually doing that. Okay, the next one here. Now we're going to talk about when an ion consists of multiple atoms. So now it's called polyatomic. So the prefix poly means many, many atoms. And so what's important here is that you never, gonna all caps this, never can change the numbers inside the parentheses. These atoms always stay together. So it's the combination of these atoms that produce a certain charge. So looking at these, it's a ratio of 1 carbon to 3 oxygens that prefer to produce a -2 charge. So you're never going to be messing with the ratio of elements to each other in these polyatomic ions. And so making a note here that atoms within parentheses act as a single particle. So just as you would say that fluorine makes a -1 charge and is a particle, you would say that CO3 acts as a particle that produces a 2- charge. And so most of these are negatively charged. But what I want to do is highlight the positive ions, which are the hydronium ion and the ammonium ion. So these are the 2 polyatomics that actually are cations. Most of them are anions. And so if we look at how they're named, most of them are going to be based on their non-oxygen atom, because as you're looking on this list, almost every single one of them has an oxygen here. So the name is based on non-oxygen atom. So carbonate is based off of carbon. Bicarbonate has a hydrogen on there. Nitrate, think of nitrogen. Sulfate, sulfur. So most of these are based off of that non-oxygen. And so what you might have picked up just from looking at the names of these is that you have these suffixes "ite" or "ate" on a lot of them. And so this refers to the number of oxygen. So for example, if we look at nitrate and nitrite, notice that the nitrite one, NO2, has one less oxygen than nitrate, which has NO3. And so typically how I remember these, so I'm going to write that ite has fewer oxygens. And the way I remember this is ite is light. My little trick here. So ite is light, it's lighter, it has less oxygens. And then 8, that will have one more oxygen than ite. So I think of like 8 ite, like an 8 ite, and grew one more. So kind of goofy, but ite is light, it's the last one. 8 has one more. So one thing that I do want to make a note of is, again, when we start writing out ionic compounds, when there's only one polyatomic ion in a chemical formula, there will not be parentheses. And so what I mean by this is if I talk about sodium hydroxide or NaOH, the two parts here are the sodium cation and the hydroxyl polyatomic anion. So notice that this is actually right up here, but when there's only one, there's no parentheses. Versus if I were to do calcium, I'll do it with the same color here. What it would look like is OH parenthesis with 2 of them. So what I'm just going to show is that if there's only one of them, one of the polyatomic ions, you drop the parentheses as well, okay? Any questions on that? I'm gonna write hydroxide.